About anything? Start. Okay, just remember we also have class tomorrow. I'll have to put the over-under. I'll have to figure that out sometime today of how many people will be here. But I will be here, and I will record the lecture. Okay, chapter 12, which may be our last chapter, but there's a lot of stuff in it, and so I have to see if Dr. Kwan's going to go to chapter or is going to go to alkynes or not. Last year, I know he wanted to stop at alkenes, so we'll see what happens. So I kind of introduced this idea on Friday, and that is that we're going to take a double bond and we're going to add to it, well, generically what we're going to do is we're going to add an electrophile and a nucleophile. And so the mechanism for this is going to be pretty straightforward. The double bond is, what's the double bond? Is it an electrophile or is it a nucleophile? It's a nucleophile because it's electron rich. The nucleophile is electron rich. So we need some electrophile in here to make these react. Because nucleophiles electron rich don't normally react with electron rich. There needs to be an electron poor in there. So what happens is that we take the double bond, and I'm going to use that pair of electrons to form the carbon electrophile bond on one of the two carbons. For this one, it isn't going to matter, but we'll talk about what happens when I have two different carbons as we go through. So for the sake of argument, I'll just go ahead and add the electrophile to the left-hand carbon, and then that leaves the right-hand carbon as a carbocation. Because remember, if you add neutral plus one species, you need to make a plus one species. And what happens is that if this left carbon takes the pair of electrons to bond to the electrophile, that other carbon lost it. And so it's at now positive charge. And then at this point, it looks like an SN1 reaction. So that the nucleophile then comes in, adds to the carbocation, so that I end up adding the electrophile and the nucleophile across the double bond. And so this is the second step in an SN1 reaction. So outside of the addition of the alkene and the electrophile, there's nothing new. This is a fairly straightforward mechanism. Now it's going to get more complicated as we go. But this is what we call electrophilic addition. So there's going to be different types of electrophilic addition. There's going to be different reagents. We're going to use the terms stereo and regioselective in their proper context. Not the book introduced it a little bit too early, in my opinion. So this is what we're going to be talking about, all these different combinations. Okay. So that's the overall generic mechanism. Now, if we want to get into specifics, the first one that we could get into would be to say, okay, let's use HBr, let's use HCl, let's use HI, and so generically, let's react the alkene with HX. And the only one missing there is HF, and nobody really does reactions with HF outside of etching glass. because HF, if it gets on your skin, it goes into your bloodstream, changes your pH, and that's never a good thing to change the pH of your blood. So the HF's only real use is to, if you put it on glass, it'll etch it. That's how you get etched glass. But we're not going to add it to double bonds. So these are the three we would add. And so again, the mechanism would be the same as what it is above. But now let's add a complication to this. Let's say that I've got this alkene, and I'm going to add HCl to it. Now, there's always going to be two ways to approach these reactions. Number one, write out the explicit mechanism. Number two, just write the products. And you're going to have to be able to do both. So my first question is always going to be, what do you add to the double bond? And in this case, you're going to be adding H and Cl. And then I'm going to say, after that, I'm going to say, what do you add? How do you add it? Which is going to involve us talking about Markovnikov and anti-Markovnikov addition. So that's the second question I'm going to ask. And then the third question I'm going to ask is, how do you add it? Which is the second question, only how do you add it? Do you add those two groups 100% cis, 100% trans, 50-50? So these are the three things you're going to have to know for every reaction. What am I adding? How am I adding it? How am I adding it? And so we're going to go through this. This makes a nice table at the end, along with regio and stereoselectivity of the reaction. So I have two carbons here that I could add the H plus to, A or B. Which one do you think it's going to add to? B? Do we all like B? Why? It's less substituted, okay. Why? Well, let's find out. Let's find out. Let's add it to B first. So I'm going to change my arrow here, and I'm going to have, let's add the H plus to B. So I'm going to form my carbocation. And so I'm going to add the hydrogen to B. That leaves me a plus charge there. How about we add it to A? So if I add the H plus carbon B, I'm going to get that intermediate. And if I add it to A, I'm going to get that intermediate. And then my chloride comes in. Oops. My chloride comes in and adds to the carbocation to form the final product. Bless you. And same thing down here. My Cl minus is going to come in, add to that carbocation to make that product. So product B and product A. So the major product's going to be which one? B? Ashton?
Because it has more stable intermediate.
Okay. So what kind of carbocation is the intermediate for B? This one's a kind of carbocation. tertiary, and what kind of carbocation is the intermediate for A. Ben? Primary. I know everybody's stunned that you almost couldn't name it because we aren't supposed to write that. But it's a primary carbocation, which we're not supposed to write because it's not very stable. So in this case, B would be the primary, or B would be the major product. I don't know that I would see any of A because they're going through a primary carbocation. Okay. So this is when you have an asymmetrical alkene, which produces two different kinds of carbocations, the major product of the reaction is going to be the one that goes through the most stable carbocation. This case, tertiary beating primary, but everything beats primary. So B would be the major product of the reaction. Now, this actually has a rule for the reaction of alkenes. And we could go let's say I had this reaction. And so there are my two products. We'll call it product A and B. And we'll say that. So my question to you is, what is the major product of this reaction? Is it A or is it B? And let me change over the class. Has everybody answered that's in this room? Okay, let's see what we've got. Okay, we've got A as the major product, 23-4, with no boths. Okay, so how did we get that? We just simply add the H plus to both carbons and see which is the most stable intermediate. So if I add the H to the bottom carbon, I'm going to form that carbocation. If I add the H plus to the top carbon, I'm going to form that carbocation. And which one is more stable? The one on the left or the one on the right? The one on the left, because it's tertiary and the other one's secondary. So then this is more stable, and so that will make product A the major product. Okay. Now there is a rule. There was a Russian chemist called Markovnikov. And so there is a rule that's named after him. This is one of these weird things where there's a little bit of a debate as to whether or not he should be given credit for this rule, because his paper really didn't say all that much about it. But then somebody went back and go, oh, well, he predicted this when he really didn't predict it. So his rule says that you're basically going to add the hydrogen to the carbon with the most hydrogens. And then the other group goes to the other carbon. I'm going to sort of broaden that out, but that is technically what is Markovnikov's rule. So you add the hydrogen to the carbon with the most hydrogens. I think that can be summarized as them that has gets. The carbon with the hydrogen gets the hydrogen. Markovnikov knew nothing about carbocations, and like I said, it's questionable. He didn't really set about and do this study and then say, oh, yeah, that's the rule. Now, I think Zaitsev did. There's not as much controversy, but people want to take Markovnikov's name away from this, but it's in so many textbooks, you can't do it anymore. So this is the Markovnikov rule, and that's what you were getting at with the idea the hydrogen adds to the least substituted carbon. Because the least substituted carbon, by definition, is going to have the most hydrogens. But the least substituted carbon is going to make a lousy carbocation. So now this all makes sense. But we still do talk about Markovnikov's rule and Markovnikov addition. So that's the one where the hydrogen adds to the carbon with the most hydrogens. Anti-Markovnikov addition is exactly the opposite. And we'll kind of get to that. So far, there's really not a whole lot new here. We're adding our electrophile, which is simple H+, to the double bond. We're forming the most stable carbocation, and then our Br- is coming in and adding to the carbocation to then give us the final product. And the more stable carbocation, the major product. Now, if you have carbocations of equal stability, that means that the reaction is 50-50. So, for instance, if I took this molecule and I just changed it a little bit and maybe put a methyl and an ethyl group there and said, now let's go ahead and add HBr to this one. Then I guess I let the cat out of the bag there by saying that you would get 50-50 when I probably should have asked you that, but When the carbons in the double bond have the same number of hydrogens, which in this case is 0, then you get a 50-50 mixture of those products. And in this case, this is an unsymmetrical alkene. So that's an unsymmetrical alkene. So in this case, we would get a 50-50 mixture. And what that means is they're both a major product. And you could go through and write the mechanism for each one. So this is HBr and H, generically HX addition. It looks an awful lot like SN1 for the second step because it is the second step of SN1. And so all of our carbocation stability rules come into play. Now we have Markovnikov's rule that will help tell us what the major product is. But not this reaction goes by Markovnikov addition. So for HX addition, what am I adding? An H and an X being a halogen. How does it add? Markovnikov. Okay. Now let's deal with the third one here. Is it 100% cis, 100% trans, or 50-50? So let's take a look at these two molecules. Do they have chiral centers? Wait, that was like 3 chapters ago. Yeah, well. This one has 2 chiral centers, correct? So that actually means, well, let me take a step back. So I just made a molecule. I made 2 products with 2 chiral centers. Now, there's a general rule in organic that says you cannot make a chiral molecule without using a chiral reagent. Okay? So each one of those, with these 2 chiral centers, let's just say for this one, there's 4 possible stereoisomeric products. There's 4 possible stereoisomers. Because I've got 2 chiral centers, 2 to the 2 is 4. And so I've got 4 possible products. 2 diastereomers, and each is an enantiomer. Okay. So that means that I could have the hydrogen and the methyl group and the bromine. I could have it added cis, or I could add the hydrogen and the bromine trans. Now, I am automatically going to get the enantiomer of each one of those products. That's automatic. And why is it automatic? Because I'm not using a chiral reagent in this reaction. So you can't make a chiral product, meaning I cannot make an unequal mixture of enantiomers unless I use a chiral reagent. And we can think about, what about SN2? In SN2, I'm using a chiral reagent to make the chiral product. In the yeast reaction that we did in lab, the reason we used the enzymes in yeast was they were of one-handed form, and they induced a chirality into the final product that we saw as being positive. Right? It wasn't 100%, but it was an unequal mixture, right? Because most everybody got a positive rotation for their yeast reduction. So the enzymes in yeast are the chiral reagent. If you don't have one of those, you're going to automatically get a racemic mixture. So what I'm really interested in for any of these reactions is, does it add 100% cis, 100% trans, or 50-50? Because the other enantiomer is automatically there. Because I can't differentiate between enantiomers unless one of these two reagents is chiral, and it's not. Okay. Does that make sense to everybody? So that third part of adding 100% cis, 100% trans, or 50-50 is never going to make an optically active product, because both of these enantiomers are going to be there for each of the products. So then I go back to my question. How does HBr, how does HCl, how does HI, how do they add? 50-50, 100% cis, or 100% trans? Anybody have any gut instincts? No guesses? Let's just work with the first product. There's the first step. And just for the sake of argument, let's say we added the H. We added the H from above the ring. That help anybody? That hint? It's not helping anybody. All right, here's the next hint. My Br minus comes in and adds. How's it going to add? Top, bottom, both? Not much of a hint? What's the second step? What is the second step of this reaction? It's the same step as an SN1. So the second step is the same step as an SN1. So I repeat my question. How does the bromine add? 100% from the top, 100% from the bottom, or 50-50? 100% to the bottom. $50-50? Anybody want to go 100% from the top? In an SN1 reaction, how would the bromine add? It would add 50-50, right? If I take a chiral molecule, I know this is review, but remember, anytime we review, it counts towards the next test. if that'll perk you up any. Whenever we take a chiral molecule and we do an SN1 reaction on it, what do I get? A racemic mixture. Why? Because I form 50-50 of the R and S. Why? Because the nucleophile added 50% to the top and 50%. The top it added 50% of the time, and the bottom it added 50% of the time. So that means the product that I'm going to make would have, if the hydrogen added on top, it'll be 50% cis, and it will also be 50% trans. So for HX addition, because it goes through a carbocation, and any reaction that goes through a carbocation will be 50-50 cis and trans. Okay? So that's going to be a characteristic of ours. Any carbocation intermediate, whenever you have a carbocation intermediate, you always get 50-50 of the cis and the trans product. So that's going to be one of these general rules. So in this case, the reaction goes 50-50. So HX addition, what am I adding? H and X. How? Markovnikov. How? 50% cis, 50% trans. Okay. So there's our first three reactions. All right, everybody with me? So you're going to be even rougher tomorrow. Okay, so now let's change the reaction. Let's do hydration. In a hydration reaction, I'm going to add H plus H2O to the double bond. Great. So I'm going to do my first step. I'm going to add my H plus to the double bond. And which carbon does it add to? To the bottom one? Why? Most amount of H's. So I'm going to add the H to the bottom carbon. And that leaves me with that carbocation, which is the most stable carbocation, being tertiary. Now I'm going to add my H2O molecule. Remember, my entire H2O molecule adds, because I'm back to SN1. And what do I form? An oxonium ion. And then what's my final step? lose my H plus, and form the final product, which is the alcohol. So what did I add across the double bond? I added an H and an OH. But I needed the acid catalyst, right? This is the catalyst. I needed the acid catalyst to make the reaction go. Because a double bond with a water, those are two nucleophiles, they won't react. So the H plus reacts and then is formed, so it's neither produced or consumed. That makes it a catalyst. So then I made my alcohol product. How did the reaction go? Markovnikov or anti-Markovnikov? Markovnikov. As a matter of fact, I'll go back here and I'll say, you know what? Whenever you have a carbocation intermediate, you not only get 50-50 cis strands, you get Markovnikov addition. Right? We want to group these things together so that way we can, if we have to memorize them, then we have less things to memorize. And how do you think the H and the water add? 100% cis, 100% trans, 50-50. 50-50, why? Carbocation. That's all you got to say. Goes through a carbocation intermediate, therefore it's 50-50. So I just add another reaction on. There's 4. But is there anything new here? Not really. Good, so then I'll add a 5th reaction on. This is easy. This is the easy hanging fruit. Right? These are the easy ones. And if you're sitting there going, I disagree with that. Anything I can do with water, I can do with alcohol. Difference between HOH and HOR. So I could add H plus and an alcohol to the double bond. And so what's my major product of this reaction going to be? What group added to the top carbon? All right, we need a voting question. So I add an H to the bottom carbon. What did I add to the top carbon? And that's going to be a word answer. So I just need you to type in the group. What group do I add up here? Give you another few seconds here. Oh no. Who else isn't it connecting for? Just you? Okay, then you get to tell us what you would have answered. OCH3. Let's see how many people agree with you. I don't know what a methoxive group is. We must have autocorrect. Methoxy, okay, check. OCH3, check. HOCH3, okay, but then what happens? OH, another OH, no. Hydroxide, no. Okay. So the group that's going to end up there is an OCH3 group in the product. If you said that you're going to end up with an OCH3H group, I suppose I'd buy that. That's the intermediate, right? So we end up with a carbocation, then the oxonium ion, and then the oxonium ion loses the catalyst to form basically an ether molecule. Okay, so again, if I wanted to write the mechanism of this, I would go back to my last page. I would erase one of the H's and put in a CH3, and I would have the mechanism. Okay, so there's, again, we've done this in the past. I know it was a while ago, but that's okay. There's always review. Right? So now I have a fifth reaction. And how would it go? If I said, what am I adding to the double bond here? I'm adding an H and an OR. How? Markovnikov, anti-Markovnikov. Markovnikov. 100% cis, 100% trans, 50-50. 50-50. Okay, so there's your first 5 entries on the table from today. But does everybody kind of see the overall pattern here? I'm adding H plus to the least substituted, the carbon with the most hydrogens, making the carbocation, adding the nucleophile. If it's a negatively charged nucleophile, it's done. If it's a neutral nucleophile, make the oxonium ion, lose H plus, get to the final product. But it's Markovnikov addition, 50-50. Okay. So now let's just make it more complicated and add a term. And this term was used in the book before, but I like it here. Regioselectivity. So there's going to be 2 terms here. Stereoselectivity and regioselectivity. So I'm going to ask you to characterize the reaction as being regio or stereoselective. Now, the first thing you need to know is what the major product is. Actually, you need to know what the possible products are. And in this reaction, for instance, the minor product would be to have the H and the OCH3 add in the opposite way, the anti-Markovnikov addition. But that's still a possible product. So in all these reactions, you can add the H to one carbon, the other group to the other, and then vice versa. The first thing is selectivity. You can't be selective if you only have one choice. Right? That's true in life. If I only have one choice, I can't be selective. So in order for the reaction to fit the selectivity rule, we need to have more than one possible product. Now, just because it's possible product doesn't mean it's the major product. And these rules about selectivity are so broad that they cover the 51.49% or 50.149.9, where you're just over the edge, all the way up to 100.0 in terms of percentages. So selectivity could mean I get 100% product. It could mean I get 51%. That's kind of a negative about these terms. So just because we're going to do reactions tomorrow where there's no possible, there's going to be 0% of that product formed. That doesn't mean it's not a possible product. So I'm going to add H, nucleophile, reverse it. Are those two products different? If they are, and I form one over the other, I'm selective. Okay. That's the rule for either one of these. But how they differ is that regioselective, the possible products need to be structural isomers. So the exact definition would be something like the reaction selects one of two possible structural isomeric products, or the major product of the reaction is one of two possible stereoisomeric products. And that makes the reaction regioselective. So this reaction would be regioselective because I'm making two different products. They are structural isomers, which means they have different names. And if they have different names, I am selecting one over the other. Again, I can select that one over the other 51.49 or 100.0. There's no difference in the rule. Stereoselectivity is when you make when you have two possible products that are stereoisomers. What are stereoisomers? Enantiomers, diastereomers, cis-trans. So for the stereoselectivity, I'm making the major product, the possible products in this case are stereoisomers, and those are going to be diastereomers, enantiomers, and our cis-trans. And so if I look at this reaction, it's not going to be stereoselective. And the first reason you might say is, oh, well, it's 50-50. Right? I can't favor one of the two diastereomers if it's a 50-50 reaction, which is true. And in this case, when I make this product as the major product, there's no chiral centers in that molecule. So I don't even have a product to select from, or multiple products to select from. Over here you might say, oh, but this has two chiral centers. Okay, great. But is it selecting one of those two diastereomers, the cis or the trans? No, it's making it 50-50. So this reaction would be regioselective, but it would be not stereoselective. So it is regio but not stereo. And here's another great rule about stereoselectivity. You're going to never have stereoselectivity if you have a carbocation intermediate. So having a carbocation intermediate makes the reaction potentially, well, doesn't make it, yeah, it makes it potentially Markovnikov. It makes it cis, 50% cis, 50% trans, which means it will never be stereoselective. So I'm introducing these terms in the last few minutes of class, which is educationally unsound. But we're going to take each reaction and go back to some of these, and we're going to go back and actually list a set of rules. Okay, when was this going to be stereo? When's it going to be regio? And we're going to apply that to every reaction that we learn. Okay, so there, I think I've loaded up the stuff for tomorrow's lecture, but I will print out the PowerPoint notes to go with it because we're going to work off those. And again, I will record it, but hopefully someone is here for me to lecture to. If you have any questions, there's also a bunch of problems in here. There's a bunch of problems in the folder.